Hello everyone, welcome to the webinar series of Mastering Microseismic and Geomechanics, the fourth webinar of this series. My name is Junwei, I'm the moderator of this webinar today. Today's speaker is Devin Garret. So he's currently involved in developing the induced seismicity and microseismic tools for IMaGE. And prior to joining IMaGE, Devin worked as a microseismic specialist for Schlumberger and ESG solutions focusing on both induced seismicity and downhole project. He has a bachelor degree in geological applied science from Queen's University. So now I'm going to turn over to Devin.
All right. Thanks, Junwei, for the introduction. And welcome, everybody. Good morning or afternoon or evening, depending on where you're listening in from. Thanks for tuning into our webinar series here. So this is the fourth part in our series, and I'll cover the microseismic image quality control and reprocessing, if necessary, of data. So as Junwei said, if you have questions, please just type that into the chat, and Junwei will get to them, and we'll probably answer them at the end, but if we see them earlier, we might take note of them sooner. All right, so just a quick outline of the webinar today. I'll do a brief review of the previous webinars in case anyone's missed them or forgotten about it, and then go into what's the next step from there, which is really QCing the data. And we'll look at a handful of different aspects to check and hopefully answer the question of, does the entire data set need reprocessing, or if it's just a select few outlying events. And from there, we'll compare the final results and wrap up the webinar for today. So previous webinars have talked about microseismics in general and really focused more on the survey design and feasibility and project setup. So that was a webinar delivered by Junwei a couple months ago. Then the third webinar in our series, again delivered by Junwei, was more about data acquisition, triggering, and then sensor orientation, velocity model calibration, and finally picking an event location. So I'm going to touch on some of these aspects again in QCing, mostly the project setup, sensor orientation, velocity model calibration, and picking and locating the events. So I'll give a brief review of those again later today. But if you really want more in-depth about information about that, please view the videos of the previous webinars. All right, so you've been delivered a data set, or you just finished processing a data set. You've got a bunch of waveforms that have picks on, similar to the one in the left, and you've got an image of your results and your events scattered throughout, like the right. So what's the next step? How do you know that these results are accurate and you can do interpretation on, or how can you analyze them to see if you need to do more QC work on them? And really, yes, the next step is to find out if you need to do any quality control. And you should do this for every project, no matter if your results look really good, similar to the image here, very linear events, clusters, they all start on zone, they'll be at the correct depth. Or if you get a project and the results look like this, where nothing's on depth, they seem to be on boundaries, shallow, or just shotgunned all over the place. Both of these projects should be QC'd and looked at just to make sure everything was done correctly. So one of the major tools for QCing is to look at any calibration shots you have. So whether that's perforation shots, ball seats, string shots, anything that's downhole near the formation of treatment, you want to make sure that these events are locating near their actual locations. So in this example, you can see perforation shots from 6 stages of one treatment well. And for the most part, they all locate quite close to their actual ports, off by a handful of meters, but nothing too significant. So this is a pretty good idea that things were done correctly, at least when processing the calibration shots. You still want to make sure that your data was processed using the same settings and picked the same way as these calibration shots. But sometimes you'll get projects where you'll have your calibration shots won't be anywhere close to your treatment well. This is an extreme example here, so hopefully no results like this, at least no final results. But you can see they're all offset from your treatment well, and that screams something's incorrect, or maybe they're just all over the place, like this example. Again, another extreme scenario, but something that just shows that your calibration shots aren't where they're supposed to be, so something has gone wrong in processing your data. So I'll go through a few of the common sources of error here and help show you what to look for if you're reviewing a data set or if you finish processing and kind of want to know what might have gone wrong. So one of the first things to check is your project setup. Then you want to look at the orientation of your geophones in your array. Check out your velocity model calibration to make sure you're using the correct velocity model for each stage. You want to look at the picking of your events to ensure that they're all picked consistently and correctly. And finally, just make sure you're using the correct processing settings from your different velocity models, your picking, your orientations, and all of that to make sure you're doing it correctly. So these are just some common sources of error. There are definitely many more, but these are some of the most common ones, and I'll go into more detail of them right now. So for project setup QC, you really want to look at the deviation survey of wells and your wellhead coordinates to make sure that everything was imported into your project correctly. You want to make sure that everything had the same units, so whether they're both meters or feet, and make sure they're both all the same UTM zone or coordinate system, so NAD 83 or 27 or anything like that. And so once you've got your wells input, you want to make sure your injection ports are accurate. So whether these are perforation locations or ball seat locations, make sure that your injection ports are at the correct depths. Otherwise, if you get first events occurring off zone, you might not know why. You want to make sure your sensor locations are accurate, so your geophone depths. If there's any array movements, make sure that you know which stages the different array placements were used for, and that that's all entered correctly. And finally, if there's any other calibration points that are used, whether they're fiber size or string shots, you want to make sure that these are correctly input into your project. Now, all of this QC can and probably should be done before the first time processing. It can be done during a feasibility stage or even just during data acquisition. You want to make sure this is all done correctly and accurately the first time to save yourself some work of having to reprocess something that was just incorrectly set up to start with. So these are common things to just double check to make sure you've done correctly. All right, so going on to actually processing the data. This slide was from Jinwei's presentation a few weeks ago, and it just talking about the fundamentals of microseismic location. I'm not going to go into much detail about it, so if you want more information, watch that webinar. But essentially, to locate a microseismic event, we're going to use the P and S wave arrivals. And the time between the two arrivals will help us calculate the distance from the receiver array. And the hodograms for both of these P and S wave arrivals will help calculate the azimuth to events. So both of these are things to kind of QC, and we'll look more at them in more detail here. So we'll start with the geophone orientation and looking at hodograms of events. So this is just a typical setup. We've got a vertical monitoring well and an offset horizontal treatment well. And when you want to QC the orientation of events, you'll plot up your perf shots and try and overlay it with the azimuths for each sensor on your monitoring well. So here you can see we've got three perf shots in gray on stage 5 here. They all locate close to zone. And we've also got our vertical monitoring well, and I've overlaid that with the blue lines, which are the azimuths from each sensor pointing towards one of those perforation shots. It's the middle one for this instance. But you can see they're all pointing pretty much directly at that perforation shot, and they're all, within a couple of degrees of each other. So it's quite a tight cluster, which is exactly what you're looking for. So looking just at this view isn't enough to really satisfy everything. You really want to check your waveforms as well. So again, this is for that same event. You can see here we're really going to focus on the P wave for right now because it's one of the easier ones to look at, but you've picked your P wave and you've put a rotation window on, which is the dashed square brackets around your waveform. And so for each individual sensor, we're going to zoom in and look at the picking of the P wave and, more importantly, the rotation window of that one. So we'll load up the hodograms here on the right. And what you want to see is a very linear hodogram right there. And if you got a lot of variation in that, then you might want to adjust your rotation window or the square brackets in our software here until you're only showing a linear hodogram, but still encompassing at least half of the wavelength, if not more than that, if possible. So once you've done that for every sensor, so you've got a fairly linear hodogram for each sensor, you want to look at the big picture and check out the azimuths for all sensors combined. Now, they should all or almost all be pointing in the same direction. So here you can see it's pretty much east-west and are in agreement. There's often one or two outlier sensors. So in most softwares, including Insight, you can just click on the hodogram and that will disable using that azimuth for any location purposes. Sometimes you get these poor azimuths if there's a noisy sensor or if that sensor is in a deviated part of the array or any other situation. So if you do have one or two over an array of 12 or 16 sensors, that's not a big deal. Just make sure you disable them before locating the event. So this is an example of a good orientation for these perforation shots. Now we'll look at what would a bad example look like. Again, this is an extreme case, and I don't expect anything hopefully would look this bad, but it might. But you can see your events are well offset. They're at about the correct distance from the monitoring well to the event as from the monitoring well to the treatment port, but they're rotated essentially from that. And again, when you overlay the azimuths of each sensor, so the blue lines over top of our monitoring well, in this case there's a much bigger spread of azimuths, so 20 or 30 degrees spread as opposed to less than 5 in the first example. So this just shows that it's not a consistent orientation and not very well done. So again, here you want to look at the individual events and zoom into their hodograms to try and refine it to get a nice linear hodogram. Here is an example of one that's not very linear, and this is mostly due to the fact that there's a bunch more noise on this event before the onset P. So if you can adjust your rotation window to try and reduce as much noise as possible and get a linear hodogram, that's perfect. Occasionally for projects, there will be one or two perf shots or ball seats that are very noisy, and so you just want to discard them from any calibration or orientation exercises because they might throw off the overall result. If you only have a couple of control shots to use, then you might be forced to use them and not have much of a choice, but ideally you'll have 5 or more shots, 4 or 5 shots, and eliminating one of them because it was noisy won't be too bad. So once you've gone through and again trying to fix your rotation windows to make them match, you again want to look at your overall azimuths. Here they're still pointing in all different directions. This is actually looking at the events from an unoriented array, so the raw data when you first import it, and you can just see how different they all are from the start. So really highlighting how important it is to get a good orientation on your array, otherwise your azimuths will just be all over the place. So this is, again, an extreme example, but it's showing how events have been essentially rotated off of the port from a fairly uniform angle from the red events, the orange events, and the pink events. And this is just, again, highlighting that it's probably an orientation issue because everything just wants to spin 25 or 30 degrees in this instance to get on zone. So that's really highlighting orientation issues. Hopefully, if you see something like this, events are at approximately the correct distance, but just offset like this, you'll notice that it's an orientation issue or a rotation window issue. Another common thing, if you're looking at the entire stage, is you might see a ring of events entirely around your monitoring well, all at about the same distance. That's another good indication that your orientation or your hodograms haven't been properly calculated or applied to your processing. So you need to go back and look at those. And again, these are fairly extreme examples, but just highlighting a point. So hopefully, so it can be fixed before moving on. All right, the next aspect to QC is the velocity model. And so again, this is a slide from Junwei's presentation a few weeks ago, but it's highlighting that as the velocity changes, so do the actual locations, as you can see on the right here. And also the further away you go, the more drastic those location changes will become from a change in velocity model. So it's important to correctly calibrate your velocity model based on different control shots, not just ones right near the receiver array, but some farther away as well. So here's an example of where I've just taken the actual velocity model and I've sped up the S wave considerably. And this is just pushes all the events further away from the monitoring well. You'd have a similar effect if I had slowed down the P wave as well. But you can see an incorrect velocity model is essentially just offsetting all of our events from where we would hope it to be. Now you can see that the azimuth from your monitoring well to the port to the event is pretty consistent through, so good indication that the orientation isn't the issue here, but it's the velocity model, and it's just offsetting the entire stage. Again, similar thing, but we're doing the opposite here and slowing down the S wave, or you could speed up the P wave, but you're just offsetting all of your events from where they're supposed to be. Here, it really highlights that even though the velocity model is incorrect, our depth can be or appear fairly correct, so it could give you kind of a false hope. Now, the depth for this scenario will be really constrained by our vertical monitoring well, especially since it's straddling the treatment formation. So our depth will be constrained by the arrival of any waves. So here you'd expect the first arrival to be about the second or third sensor from the bottom. And no matter what you do to your velocity model, that will still constrain your depth to an extent. You know, as you get further away, these green events, there is more uncertainty in that. But for a vertical array, the move out will really help constrain the depth. If you have a horizontal array or a deviated array, then that's not necessarily the case, and you could have a velocity model that will also affect your depth a lot more as well. All right, so to go along with velocity model calibration and orientation, you really need to make sure that your events are correctly picked, and also any picks or however you pick your events for your calibration is the same way that you're going to pick your events for any processing that you do. So this is just an example of a waveform. It's a pretty nice and clear waveform. You can see a few different phases, like the P here. We've got one shear phase here and a secondary shear back here. And so we'll just put on a P and in this case an SH wave. And one thing we can do is rotate it to the direction of particle motion. So in our software insight, that will change everything in the in a P direction to be red, in a shear horizontal to be blue, and in a vertical to be black. And doing this can really highlight if you've likely picked the correct P phase as it tries to rotate towards P typically. But if you had, some blue or some red showing up in your SB here, it'd be a sign that maybe you're not rotating it properly or picking the correct P wave. Or conversely, if you got some black or some red in the SH here, maybe you're not properly picking the P again. If your two shear phases are overlapped, then you would expect blue and black, the blue and black phases in this image to be overlapped. So that's fine, but you still would expect minimal P energy or red wave to be overlapped with your shear. So that kind of helps. Another strong tool that Insight has to help confirm your picks and also your event locations is the ability to generate synthetic waveforms based on different locations or event locations. And so here's an example. It's the same event on the left and right, but it's being located at two different points. So the original was located shallower than the reprocessed image. But so a synthetic waveform has been generated for both of these theoretical locations, and the synthetic record has been overlain with the recorded record. So the synthetic is the blue trace, and the recorded is the black trace. But this really helps identify that, in the original, your modeled and your actual picks, so these light blue and dark blue picks, aren't lining up at all. So the dark blue is your modeled, so if the event actually occurred there, that's where you would expect your picks to be, not further out like this. And you could maybe see, a P arrival matching your synthetic, so you can question it there. But if you look at the shear component, you can really see an offset in time between your synthetic shear and your actual recorded shear wave in terms of time. So that's a red flag that this event has not been accurately located. In the reprocessed version, where we moved the event down several meters, you can see that everything matches up quite nicely. Our modeled and our actual picks for P line up quite nicely. And more obviously, the shear wave, we've got the first shear arrival for both the modeled and the recorded data matching very nicely in time. So this just gives us a high confidence in our results for the reprocessed data and also in how we pick the data. This has also helped us identify that there's a bit of a head wave or refracted wave in the recorded data. So you can see probably the direct wave is this larger P arrival coming later, but there is a bit of a signal beforehand, which is sometimes hard to pick up and is actually a refracted wave that our software is trying to locate. So just some more examples showing recorded data and the uses of synthetic. This is a fairly clean and a bit more obvious waveform, but you can still see how closely the real wave, which is the top one here with a bit of noise before the event, and the synthetic, the P and the S both match up quite nicely. So it really highlights that our picking and our location is accurate and correct. So you might not need to generate synthetics for every event, such as this one that's more straightforward. But some events have more complex waveforms. So you might have a bit of, or some reflections coming off of different layers and some refractions or head waves. So here you can see, a few different P waves coming in, and the same with shear. And so the ability to generate synthetic waveforms really helps identify where you should be putting your first picks and how you should be picking and locating your events to ensure that all phases are matching for your synthetic and your actual recorded waveform. And it just gives you that added boost of confidence that how you're picking the data is correct. So another very useful tool that should be used. All right, so now that you've covered the picking, the velocity model, and the orientation QC, you want to make sure you're using all those techniques that you've looked at when you're actually processing the data. So you want to make sure your processing setup's correct. And really you want to make sure you're using the correct geophone array and orientation for the given stage or time frame, and the same with the velocity model. So there might be several different velocity models used throughout your project if your geology is changing, or if there's faults in the way, or you're recording through areas of rock that have been previously fracked with previous stages kind of thing. So it's quite common for velocity models to change throughout a project, slightly, not drastically. And also it's possible that you've had an array move throughout your job, whether you're just pulling it up to make it shallower, or if it's a lateral array that you're pulling along a horizontal well. but you want to make sure you're using the correct geophone array for the stage you're about to process or the time frame you're about to process. You want to make sure that any automatic picking algorithms are properly set up. So if it's going to look for head waves and refracted waves, or if it's only looking for body waves, you want that to be noted and to be working. And you want the hodograms and the source vectors to be accurately calculated, so making sure that it's linked to a P or S pick and the time frame that you're going to associate, so essentially the length of a complete waveform for your P or S window is going to be used. Or if you've got really noisy data, maybe you want to shorten up your hodogram to really just get the P waveform and try and eliminate as much noise as possible. Or maybe you want to make it longer if you've got a clean waveform to clean things up. And finally, you want to make sure your location algorithm, whether it's a simplex or Geiger or something else, is properly set up and working. So in my opinion, before running your processing algorithm on an entire stage or an entire data set, you want to select a handful of events, 5 or 10 events, and just run it on these individual events to make sure that it is going to correctly pick and locate your events first before running it for a few hours or days, depending on the size of your data set, only to come back and find out that it wasn't correctly picking or wasn't using the correct velocity model kind of thing. So make sure you just test it on a couple of events first, and then when you're satisfied that it's working, you can run it for the entire data set. So that kind of covers the broad aspects of any QC you want to do. And if you've noticed any issues in the final data set with these aspects, there are hints that the entire data set might need to be reprocessed. I've primarily just shown examples using calibration shots so far, but you will notice the same problems if you're looking at an entire stage worth of data. If the velocity model's off, incorrect, the entire stage may be offset from your treatment well, or it could produce, kind of a ring or even part of an arc around your monitoring well if it's an orientation issue. So if you notice any problem for any of these things, then that's when you'll want to get your data set entirely reprocessed. So conversely, you might get a final data set that looks similar to this, where the stages are all clustered together nicely. They're on the treatment well. There's nothing super obvious that looks incorrect, and you've gone through the previous QC measures and everything looks good. So you just want to do a QC of some individual events. Maybe you got some outliers, like this cluster of 3 events out here. This project doesn't have a lot of really shallow or deep events, but maybe you just want to look at a couple of these deeper or shallow events to make sure that they actually are there before doing any interpretation based on them. So that's fairly straightforward to look at, and we'll go through a few steps on how to look at individual events to make sure they are where they are. So here's an example of an event that is outlined from the main cluster for the stage, and it's about the same distance from the monitoring well as the main cluster, so it's hard to look for PS separation, but it is at a drastically different azimuth. And so what we can do is we'll take some events from the main cluster and we'll look at their azimuth, and for this example, this one's at about 90 degrees, 93 degrees hodogram, and then we'll look at the outlier and make sure that all of the rotation windows and hodograms are in agreement. Most of them are pointing kind of south, and it's locating south of the monitoring well at an azimuth of 162 degrees. So this is just confirming that your event is actually locating where it should be. All right, so the next thing you might want to look at is outliers in depth. Again, this project didn't have anything too crazily shallow, but it did have a bit of deep events, so we'll be able to compare something that's shallower on depth to some deep events. And this method is really only useful for using vertical arrays, but to determine whether the depth of events is accurate and correct, you really want to look at the move out of either the P or the S wave. I typically look at the S wave just because it's going to be more pronounced than the P, but they'll both show the same feature. And really what I'm talking about there is you want to look at the difference in time from your earliest arrival of the shear wave to the latest arrival. So in this instance, something that's shallower will have a smaller move out versus something deeper will have a higher move out. Additionally, this project, it's got a bit of a funky velocity at the bottom, so that's why it's not a nice hyperbolic or parabolic curve, but it's got a kind of an S-shaped curve at the bottom. But for any vertical array that straddles it, if it's a clean arrival, the parabolic arrival of the shear wave will help determine the depth of an event. So whatever sensor you get in your first arrival on, so here it's sensor 9, that's a good indication for most projects, not this one because of the different or intriguing velocity model, that around the depth of sensor 9 is where your event should locate. So if we had, for example, an event locating up here, we would expect the first arrival to be on, sensors 2 or 3, somewhere in that vicinity. And that would be a good indication that that event is at that depth. But otherwise, looking at move out really for a vertical array really helps constrain the depth. So another visual thing to look at are just events that are locating a lot further away or a lot closer to the monitoring well than the main cluster of events. And the best tool to look at this would be the PS separation, so the amount of time between your P wave and your S wave arrivals. So here you've got, 2 events that I'm showing waveforms for, one in the middle of the clusters and one further away, both with roughly the same azimuth, so they're kind of both, just east of the monitoring well, maybe a bit northeast for the further one, but our PS separation is vastly different, almost double, so you'd expect our events to be close to twice as far away for these further events, giving justification that we do have some activity occurring that far away from our main cluster. So one final thing to look at for individual events is the signal quality itself. And most companies, including IMaGE, have an output that they call confidence factor. So it's an attribute that we give to each event, and it's on the scale of 0 to 5, with 5 being an excellent event and 0 being a terrible / one that shouldn't be located, or it's very poorly located. And so you want to look at some of the lower quality or lower confidence events to make sure that they are being accurately picked and located. So the confidence factor is really, it's made up of the P and the S signal to noise ratio. So if it's a very noisy event, it's going to have a lower confidence factor. And there's not a lot that you can do in processing to fix that. You can try and develop a better filter, but beyond that, if it's a noisy event, it's a noisy event. But the things that you're more able to kind of fix as a processor is looking at when it says P and S picks here, it's talking about the residual between the theoretical arrival for its location and the actual pick. So the residual amount of time in milliseconds between those 2 picks. If they are pretty much right on top of each other, or there's no residual, you're going to get a value of 1. And if they're far apart, signaling that the location, the actual pick is not an indication of the location of that event, you're going to get a 0. And the other one you can look at is the direction aspect, and that's looking at the hodograms and the azimuths for each sensor. And so if they're all in agreement and they're all pointing towards where the event's located, you're going to get a value of 1. Whereas if they're all kind of scattered all over the place, like in the right hand here, you're going to get a value closer to 0. And so to get the actual confidence factor, we're just summing up these 5 different aspects on a scale of 0 to 1 to get a grand scale of 0 to 5. And filtering for only events that have high confidence factor, so above a 3 or above a 4, for instance, will give you a good indication of exactly where your trends are in your data. And conversely, if you filter for the low confidence factor events, you can filter at ones that maybe you want to go and revisit, or if necessary, remove from the data set before doing any interpretation. And so this confidence factor is something that we provide with any of our data sets at IMaGE, and several other companies do this as well. But if your data set doesn't have a confidence factor, something that you can kind of look at is location error. So if there are any events with anomalously high location error, it's an indication that maybe the picking or the azimuth direction or the signal-to-noise ratio is very poor for that event. So you want to either filter them out or go and look at them again to see if you can improve those aspects of the event before processing it. So that is, in a nutshell, kind of what to look for when QCing individual events. And before it was looking at projects as a whole. And so finally, when you've QC'd it, and if necessary, reprocessed any results, you want to go back and compare your reprocessed results to the original results to make sure that the improvement does make sense and that everything is where it should be now. So even though it's reprocessed, it always helps to go back and kind of QC things again. Hopefully it should be really quick and easy to do, but you want to make sure that things are still correct. So here's an example of a project that the first pass of processing was incorrect. You had a lot of shallow events, might have been located on a grid boundary or velocity model boundary, or I'm not too sure what happened. But anyways, nothing happening on zone, especially near the toe of the well, so red flags that something's wrong there. And we went back and reprocessed the results, and you can still see a lot of that vertical growth upwards, but at least now there's a bunch of events happening near zone. And if you were to play one of these stages in time, you would see the events start at the treatment well and grow upwards. So all the early events for the pumping stage occurred down near the treatment zone, and the later events are shallower. So it helps to show that the reprocessed results are likely accurate. And again, in looking in plan, the original results, there's a lot of scatter in them, not a lot of obvious trends for the stages, especially further out towards the toe of the well, which is at the south end of the screen. And the reprocessed results show a lot more unique or uniform trend for each stage, and each stage is separated to the area where it should be, so high confidence that the reprocessed results are accurate. All right, so just a brief wrap-up. Every project should be QC'd after processing, just to make sure that everything was done correctly and hopefully to identify any reprocessing if necessary. The common problems that are seen, in my opinion, are project setup, make sure everything was input properly, geophone orientation to make sure that each array position has been properly oriented, velocity model calibration for every stage or every area is accurate. You want to make sure that you're picking consistently throughout the data set and using all of these things I just mentioned in the processing algorithm as necessary. And then finally, once you've got the bulk of the data set correctly processed, you can QC individual events based on if they're outliers or if they've got poor confidence factor or high error. And then hopefully your finished reprocessed results will give you a lot of confidence to move forward and start the interpretation with. So with that, I would like to just mention our next webinar that's going to happen at the end of August here, and that's focusing on data interpretation and really trying to recognize biases within the data set. So please join us for that one and stay tuned for it. Thanks everyone for watching.